Okay, hello everyone. I think I am recording. Yes. Okay. Hello everyone. Since there are not many people today, we will do the evaluation of the teaching evaluation next time, so that there will be more people, hopefully. Yes. Yes, I did. Good. Yes. So we will do the evaluation, teaching evaluation next week, which is the last class for this module of the course. What do we do today? Okay, today we will do something. I believe the most interesting, let's say, topic of this course, which is supervised learning. The idea of today's class is to, first of all, finish the previous class, which is about regression, basically. So implementing regression from scratch using the stochastic gradient descent and gradient descent. Then we move to supervised learning with classification. The idea is to get to the point where we implement a very simple neural network from scratch. So the idea is to implement a neural network for binary classification using NumPy from scratch, and train the neural network using stochastic gradient descent or ADAM. That's the idea of today's class. Just a quick recap from last class is that what we have now in practice is we have a parameterized model, parameterized machine learning model called f theta of x, whose specific form will be provided in this class. We have a loss function, uppercase L theta, depending on the data set xy, input that data. And such that this loss function can be decomposed as the summation of simpler terms, in this case the square norm of the error, so that the gradient of the big loss of the uppercase L loss function can be computed using the gradient of each component lowercase l. In this setup, we can do stochastic gradient descent, which basically is very, very similar to gradient descent, but instead of just computing the gradient of L and performing one step of gradient descent, we repeatedly sample a mini batch, which is a subsample of the data. We compute the gradient of this mini batch, and we update the loss function on that mini batch. And we repeat a given amount of time. Okay. The idea of the first part of today's class is to conclude with this exercise called, which in my website is called multilinear regression with CDN and SCD. Basically, the idea is I want to download the dataset from Kaggle, using the link provided, and we will try to perform a complete exercise of machine learning from data to data processing to developing an algorithm, training the method and testing the method. So what I want you to do, first of all, is to download from this website, if you didn't do that last time, download from this link the dataset. So you click on the link, you click on data, you scroll down, and you download all. In the meanwhile, I will open my VS Code. Okay, I will download the data, so click download all. You should find a folder containing a few data sets We won't care of all of them. We just care about train.csv, which, as you can imagine, is a training set, and the test.csv, which is the test set. So let me take these two and copy paste them. So I copy them. I go into my working folder. I create a folder named data, and inside of it I will paste my data. So that's the setup you should have if you want to follow what I do step by step. So you create a notebook. In the same folder of your code, so on the left-hand side, you have a folder named data, which inside contains two data sets, which is the train set and the test set. Okay. Starting from here, we can go back to the theory. So, let's talk about the problem. What we have is a data set containing multiple features to predict house prices. So, if input information about house prices, in particular, we have three data: lot area, overall quality, and year built. So, it's three input features you can use to predict the price of the house. Clearly, the output variable y represents the price of the house. What we want is to build a linear regression model. Now I believe that now you did something with Elena Piccolomini about that. So how does it work? We define our model f. This should look like something you already know. So you define your model f theta of x to be theta, parameters theta, transposed x, where theta represents the parameters theta 1, theta 2, theta 3. So it's the three parameters that identifies the linear regression model, while x is the input vector, which is three-dimensional. Okay. So the first step that I want you to do actually is to pre-process the data. So the task is we already download the data. We want to load it into memory, and we want to extract from the data the input columns x and the output column y. So I'm not sure I don't think I told you how to load the data into memory. So I will help you with that, and then I will let you try to do everything else. So let's start by importing NumPy as always, and importing pandas. Pandas is another library we didn't really told about. I didn't tell you anything about. It is a library designed for working with data sets. You will use it a lot in the next few teaching course during your master degree. For my course, it's not that relevant because we don't want to work with matrix and vectors, not with data sets. But we needed to load data into memory. So just to do that, let's call train data, and the function is pd.readcsv, and inside of this function you should insert the path, the relative path of the data. In particular, here in my case, it is data/train.csv. So in this way, we load into memory the dataset contained into the CSV file, and we name the dataset as train data. We can check by printing train data.head. We can check how the data is. So this is a complete list of all the columns of the data and the first 5 rows of this data set. As you can see, there are a lot of information. Some of them are, for example, this one is the dimension of the frontage, the dimension, the area of the lot, the street where it is, as you can see, there are some nonce, for example here, some NaN values, and other variables, okay, we don't really care about. Now, if you follow my class on how a machine learning project works, you should see that a first step in designing a machine learning model is to pre-process this data. Pre-processing means removing everything we don't need, removing nonce if you have some nonce, because these nonce, this means not a number, so this is a missing values. So removing missing values, process the strings. So for example, here we have a lab contour, which is a string. So we want to process the string to embed it into numbers so that we can work with them, and split between x and y. In this specific project, I don't want you to work with all the variables so that we can make it easier, and I want you to only work with the subset of the columns. In particular, what I say is here is that we only want these three variables, which is lot area, overall quality, and year build. So we can extract them into x. So it's x should be, I don't remember if I can do that. Yes, let me do that. Let me create a variable called input calls. So into input calls, I will list all the columns I want to extract. So lot area, overall quality, and here build. And then I want to extract from train data the columns. I don't remember if I can do that, maybe. I don't remember which function. Give me one moment. I have. Okay. Yes. I will do copy and paste it. Okay, so I copy and paste the solution so it's faster, but so basically what I do is I load it into memory with the array function from pandas. Then I list all the columns that I want to extract. The column names are my website, so dot area, overall quality, and year built is the input columns I need. And then I just extract from train data the features, and I place them into x, which is the input variable, and sale price, which I put it into the y variable, because it's the output variable. Note that I did something. Let me run this code for a moment. Okay. Note that I did something. Okay. This one, okay, it's pretty intuitive what happened. Okay, I just loaded the relevant columns into memory. The dot values extract only the column, only the table itself, ignoring rows and column names, basically. But what I did here, it is interesting. For the variable y, what I did, I reshaped the variable into shape -1, 1. I don't know if you can guess what this function does. It is a weird behavior of NumPy, so I just want to explain it, even if it's not necessary to be able to use it. But the -1, when you call the function reshape in NumPy, that's NumPy function, NumPy methods, the -1 value inside of a shape means find it yourself. So whatever you have, whatever you need, it is a way to tell NumPy to automatically fill this value for you. So y is a vector of shape uppercase n, where uppercase n is the number of data points we have. So let's say y is a vector of shape 1000. By default, uppercase y is what we call like a mathematical vector. So it's a one-dimensional vector of shape 1000, comma, or whatever, comma, uppercase n, comma. We don't want to work with uppercase n, comma vectors. We want to work with column vectors. So we want to make this uppercase n, comma shape into an uppercase n, comma 1 shape, so that it becomes a column vector. So what this function does is reshapes the uppercase n, comma vector into something with shape whatever, the minus 1 is whatever, 1. So this whatever is automatically computed by NumPy to be the only possible values that does not return an error. And so in this case, minus 1 is uppercase n. So at the end of the day, this operation just basically takes the shape of y and returns a vector with the same shape, but it's a column vector now. So let me show you in practice. So let me comment this and print the shape of y. So that's the shape of y. So the y is a one-dimensional vector of shape 1460, comma. We don't want to work with this. We want to work with a column vector. So what we want is to add a 1 after the comma in this shape. Doing that, what happens is that it says, okay, we need to have 1. We need to have 1 in the shape. The other value of the shape, choose it as you want. And the result is that the only possible value that if you put it instead of minus 1, you don't get an error, is 1460. Okay, that's how NumPy works. Okay? As I said, you don't need to know that, because you can also explicitly write shape of y instead of minus 1. But if you will ever check code online on Google or on ChatGPT or whatever, this is going to happen. So sometimes you will see this minus 1, 1 into the reshape. So you need to know what happens. Okay. So we load the data into memory. We selected numerical columns we were interested in, and then we move to a very, very important step: normalization. I don't know if you already did something about that with the column. Maybe yes. But while doing machine learning, it is crucial to normalize your data. Why? Because this is something I said last time. Let me show you some value of x. Okay, that's our input data. This is a matrix with 3 columns and 1,000 approximately of columns, of rows. As you can see, the first column contains values in the range of 10,000 approximately. The second column contains value of the range of the unit. The third column contains of the values of the range of 1,900 or something, 2,000, because that's the year. By default, if you don't do anything, if you don't do nothing, the code assumes the first column is more important because it's higher. Okay, so clearly 9,600 is higher than 6. So the first column is more important than the second one by default. Let's say this is a bias we don't want to insert in our code, because this would completely destroy the performance of our method. You will see, and you can try if you want, that if you try to optimize a model without normalizing the data, so you just take this data and you train your model, you will get very, very bad results. Your model will stuck at some point. So normalizing the data assures that all the variables are pretty much the same value in terms of like magnitude, and so by default each column is as important as each other. Let me show you how to normalize. So that's how you usually do that. So this is something you see actually in every probability or statistic class. So to normalize the data, what you want to do is you take your data set, you subtract the mean, and you divide by the standard deviation. This is only one of multiple possible ways of normalizing the data. This is the only one we care about in this course. But just to tell you, there is something called min-max normalization, there is something called linear normalization, or -1, 1 normalization. But I don't want to go in detail because it's out of the scope of this course. What happens here is that the resulting model, the resulting data set, will have a mean of 0 because we subtract the mean, so the mean is 0, and the standard deviation is 1 because we divide by standard deviation. This way, our data looks like a Gaussian. Okay, should look like a Gaussian because it has the same mean and the same standard deviation of a Gaussian distribution. Indeed, if we now print x, as you can see, now the three columns are comparable in size. I mean, all of them are in between -1.5 and 1.5 approximately. And in general, this one now is 0.15, this one is 0.07, 0.98. All of them has different magnitude based on the value of the variable, but they are comparable in size. So there is no bias anymore in the data set. And that's what happened until here. To get what's happening here, let me go back to the theory one moment. Okay. This is something you should recognize. Okay. That's our linear model. So f theta of xi is our model, defined as the summation j going from 1 to d of w times x plus b. This is something you should know because it's something you already saw with the Nappicomi. That's a linear model. This is something we don't really like because it is very complex to work with summations and stuff in Python. What we want to do is to convert this into matrix form. How to do that? That's a trick. I don't know if you already saw this trick with Elena, but what happens is that if you take your data x and you prepend just before the data a vector of all ones, so you artificially prepend a vector of all ones, obtaining what I call here x tilde, defined by all ones and then x. What happens is that now theta transposed x tilde, since the first value of x tilde is 1, it results into this, which is theta 1 plus theta transposed x not tilde. This structure is exactly our linear model with bias that we have here, is this one. So this is to say that if you want to work with matrix, so you want to make everything linear working with matrix, a technique to add bias is to synthetically create a vector of all ones as the first call of x, and using x tilde instead of x as your data, allow your model to simulate a bias term. Okay, that's the math if you are interested in that. So f theta of xi is equal to theta transpose of x tilde. X tilde is this one. So it is equal to theta transposed the vector 1 comma xi, because 1 is what we added synthetically here. This transposition results into theta 1, because it's theta 1 times 1, which is 1, plus theta, all the others theta 2, d plus 1, so all the thetas, times xi. That's the linear model with bias that we had before. Okay, that's a very common technique, okay? That's something you will see every time you work with data, and every time you work with linear regression, or even polynomial regression, or multinomial regression. It is something pretty common to have. So that's what we did here. So this function here prepend a vector of all ones, as you can see, to the matrix X. So the first column is now all ones, and then you have X. Now, as a result, if I print X now, oh sorry, I closed. Now, if I print X, what I have is the same data that I had before, so with numbers, and the first columns are all ones. Remember not to normalize your data after you add all ones, because if you add all ones and then you normalize, you are trying to normalize something artificial, so a column of all ones. That's artificial, and this creates actually a mathematical error, because you try to divide by the standard deviation. Standard deviation is 0 because all the numbers are equal, and this creates a mathematical error. So avoid dividing by the standard deviation, and normalize before you add the bias term. And that's it. Okay, that's the final step of our data cleaning process. As I said, this is a crucial step for all machine learning model. Sometimes it's the hardest step in the machine learning model. In this specific case, I gave it to you all the processing, because that's not the focus of our teaching course. It's going to be the focus for the next, like for Andrea Sperti course, for example, in deep learning next semester. Okay. So, given that, so now we have our data, we have our x and y data. What we want is to implement our stochastic gradient descent algorithm to solve this problem. So what I want, if you remember from last time, let me show you. Okay, last time we had this algorithm. I don't know if all of you still have this algorithm with them. This was our implementation of stochastic gradient descent. Let me copy paste it. If you have it, you can copy paste it. If you remember, this function takes as input a loss function, the gradient of the loss function, the data xy, a starting value at 0, learning rate by size and number of epochs, and run the training all over the iterations until convergence for our model, returning the final parameters. Okay, what I want you to do now, similarly to what we did last time, is to implement a loss function L, taking as input theta, x and y, and a gradient of L, theta, x and y. You will say, okay, why should it be different from last time? It is very, very similar to what it was last time. Now there is a difference, because we are working with matrices, so in the matrix form. And so this is the function we actually want to implement. So last time we was working with a point-wise function, so we had these like summations and multiplications and stuff. And now we have a matrix X, a parameter vector theta of a given dimension D, and we want to implement this function for the gradient of the loss function, okay, which is exactly equivalent to the function we had last time for the gradient of the loss, but now it is in matrix form. Why? Because this is the way you usually work with data. You usually work with matrix form. And that last time we was working with summation because we didn't do that with data yet. You didn't study maximum approximation and stuff. Now you know it, so you can work with matrices. It is not hard in practice, but you need to be able to implement this gradient by your own in NumPy. So let me help you with L. So the last function L is the squared norm of the difference between our prediction and Y. Let me give you the solution and minus. Okay, that's the loss function. Why? Because x times theta represents the output of our model. So x times theta is the output of our linear regression model. This should not be surprising for you because this is exactly what you did multiple times with Elna. It's just matrix times vector multiplication to simulate a linear regression model. Minus y because it's an error. You take the square and you take the average. That's the loss function. Now, based on this, I want you to implement the gradient of the loss. It is easy, so I give you like a couple of minutes. You just need to implement this function here, inside of that grad L function. If everything is fine, your SGD algorithm should work out of the box with this function. So you just run your algorithm and it should work. By
We have some problem with pandas.
what happened?
I'm not sure.
So is anyone working on like lab PC on the PC of the lab? Raise your hand who is working with the lab PC. Is someone able to import pandas? Okay. Let me think if there is a solution. Maybe with NumPy we can import the data. Let me check. There is an issue with the installation of pandas, I believe, from the technicians. Wait a moment. Let's try a solution using NumPy. Google says that we can do something like import NumPy as MP and then train data mp.gen from text. Okay. This kind of work, now we need to find a way to extract the columns we need. But at least it is kind of working. So if you work with pandas is better. But if you cannot work with pandas, you can use this numpy function. Now let me check how to only take 1, 2, 3, 0, 1, 2, 3, 4, 4. Wait a moment, I'm doing some test. I think I read it wrong. I'm trying to count the column ID. 0, 1, 2, 3, 4 is okay. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 17. Ci siamo. Okay, this should do the work. Let me find y. Meno 1. Okay, if you cannot import pandas, you can write these lines of code. Now it works. These should load the data. Let me copy paste this on the previous cell so that you have both the version. Again, pandas is better in general. So this block here lead to exactly the same result as the block just above. Everything else you need to do that by yourself. You just need to copy to write it down. So let me go to this point. So again, if you are able to use pandas, it is better. If you're using the PC machine, you should use. You can use this alternative. It is a technical problem depending on the PCs, the inability of loading pandas. Okay. Also, if you did that, I think you can go back. You can go back to this point. So now try to implement the Gradient Vel. Now really try to implement the Gradient Vel based on the function on my website, which I now show. Okay, now we get the solution. So we just need to copy basically this definition. So we have inside of this bracket is x. Inside of this bracket is x times theta minus y. So it's x times theta minus y. Then we left multiply by x transposed. And we multiply by 2 and divide by x dot shape 0. So that's the solution to this. So now we can try to execute this function as you did. Or probably there will be a couple of errors, but we will solve them. We will solve them in case, just in case. So let me define. So we already defined the theta. So we already defined L and grad L. We already know x and y, which is our data. So let's define theta 0. Theta 0 is mp dot 0, so we initialize it to be 0. We shape 4 comma 1 because we already say that our vector theta should be a 4-dimensional vector from the theory, from here. I don't remember what. Here, okay, that's a 3-dimensional vector for the axes, because there are 3 axes, and 1 dimension for the bias term. If you want to automatize this should be x dot shape 1. So it's the number of elements in x. And then we can run the code. So the code is theta epochs equal to SGD of L, grad L, which is given, x and y, which are given, theta 0, which we defined. Learning rate, let's set it to 10 to the minus 3. That's a common choice for this kind of algorithm. Batch size equal to 32, for example, and the number of epochs, like 100, for example. Okay, now let me, yes, sorry. I did an error. Here, you need to return this, of course. I forgot to return, so you need to return the value of the gradient. Yes? Okay. I don't know if you noticed that I ran the code twice. Before there was like a warning. I cannot recover it now, but there was a warning here saying overflow value encountered in subtraction. Why is happened? It is because in the previous execution, I forgot to normalize x. So I didn't run the code to normalize x and y. So, if you don't normalize it, the code is not converging, it is diverging, or it went to plus infinity. That's why you get an error of overflow. So, if you try to comment normalization, you will see that your algorithm will diverge, will go to infinity. Okay, so now we train our model, but we have no idea how to use it in practice. How to do that is actually pretty easy. So first of all, we need to slightly modify the stochastic regression function to add one more feature that we need for the final version of our code. That is, at some point, and you should do that now, at some point I want you to save the value of the loss all over the iterations. So my idea, what I want you to do is to modify the algorithm so that you save the value of the loss during iterations so that we can visualize in a plot the behavior of the loss function while the train goes. Okay. That's not hard. That's pretty standard to do. I think it's the first time we do that in this course. So the idea of saving the behavior of a value all over the iterations. It is not computationally difficult to imagine how to do that, but hey, maybe you can have some trouble. So I give you like 1 minute, 2 minutes to try to do that. Okay, so I give you the solution. The solution for that is we create a list. Okay, that's I will give you the basic solution that you can get if you, for example, ask to ChatGPT. That's not the most efficient one. I give you the efficient one as well in a moment. So the simplest possible is to initialize a list called the loss val, and after each step here, you update the loss val. The loss val list. So it's a loss val dot append. We compute the loss function L over theta x and y. Now this is a choice you can do. Like you can either use x and y here or xb, yb here. So you can compute the loss function over the batch or over the whole data, basically. But for me, it is not that relevant, this exercise. You can also use x and y. In real practice, you usually use xb, yb, or you do some technique called accumulation of the loss. For now, we just stick with x and y. And then we return loss val. So here we have loss val. finally, as I said, we can visualize this loss. So we can visualize the loss. It is not hard. I will give you the code, but so we import matplotlib. The command is plt.plot loss val plt.grid, let's say alpha equals 0.3 plt show. Okay. And that's it. So what happened is that what we can see here is what we expect to see every time, actually, which is a loss function decreasing, continuously decreasing from the highest value, which is 1 in this case. Okay, 1 is what you expect to have as a starting value when you normalize your data. But you can do also differently, it's not like a constraint. But the loss should go down very, very, very steeply until like a tenth of the curve, basically. And then it still goes down, but basically stabilizes. That's the behavior we expect from our training. As you can see, the number of steps is huge in this case. The number of steps is about 4,500. If you remember, in the gradient descent experiment, we saw a number of iterations of about 200, 300, 100. While here, the number of iterations is of the order of thousands. Sometimes it's going to be of the order of millions. That's one of the advantages of SGD, which is since we, for every epoch, so for every full view of the data set, you iterate multiple times, one per batch. Computationally, you are doing a lot of steps for each complete step in the data, for each epoch. By basically 32 is the batch size. The data set is 1,400, sorry. So it's about, I don't know, like 50 iteration per epoch. So that's the story. So what's happening here now is that we have a model. This model has been trained on a training set, and the loss function is decreasing. How can we evaluate this model? How can we visualize the output of this model? Let me give you another slide with visualization of the output. Sorry. No, we cannot visualize it, sorry. It's three-dimensional, I didn't think about that. So yeah, the behavior of this loss means that our model is actually learning something. It is obtaining something of the order of 0.35. So the error is of the order of 100. So we are pretty good. We are pretty good in estimating the quality, the price of the house given our variables, our input variables. But that's the simplest possible algorithm you can imagine. Okay. We want to move from this point to something more interesting, because linear regression with SGD is too basic for us. And they want you to extend this topic into two directions. First of all, and this will conclude this section, is changing the algorithm. Because if some of you have already heard about of machine learning in general, you would know that SGD is never used. No one uses SGD. Usually you use Adam. So what I want to do is demystifying Adam, basically. So I want you to give the implementation of Adam from scratch, just to identify what are the features that makes Adam so good in practice, and test Adam on this setup. So what we want to see is if Adam is better than SGD in training, basically. Okay, what is the biggest limitation? What is the biggest limitation of SGD? or in general of stochastic gradient descent or any other algorithm on stochastic algorithm working with batch. The biggest issue is that we cannot adaptively change the learning rate. So what we did in our code, as you can see, is that here we fix the learning rate to be 1 minus 3. That's given, that's fixed. And we never change this value for the whole training. We already saw in gradient descent that's a bad choice. In gradient descent we had the backtracking. Backtracking was very good in identifying the optimal values of learning rate that actually bring you to a minima. We cannot execute backtracking in stochastic gradient descent because we cannot compute the gradient on the whole data set, which is required for backtracking to work. Therefore, we need another technique. And that's the idea of ADAM. ADAM, standing from adaptive moment estimation. As you can imagine, adaptive means that the learning rate of ADAM adapts during execution of the training. So, basically, like, from a very, very far perspective, ADAM is exactly equal to SGD. There is no difference in compared to SGD. So you have your data set, you take one batch of your data, you compute the gradient of on the batch of your data, you perform one step of the algorithm, and then you repeat this process. It's the same thing, but now what changes is that we modify the step size, we modify eta k during iteration based on, let's say, based on how fast we are moving. So that is the following. The intuition is the following. We will start with the classical gradient descent as the algorithm until we stuck. We stop decreasing at this point. When you stop decreasing, the algorithm automatically finds that you are stuck and reduces learning rate to go more into detail, basically. Because what's happening here, we are horizontals because we are close enough to the solution, and you cannot move closer to the solution. So we want to reduce the learning rate so that the steps are smaller and you can move closer and closer to the solution. That's the very general idea. How it is done? This is done by computing these two quantities, mk and dk, which is it's called the cumulative mean and cumulative variance of the gradient. The technique is called EMA. You will learn about EMA multiple times in your future. In this case, you use so EMA is basically an average, so a weighted average between the previous mean and the actual mean, the actual mean, and an average weighted average of the previous variance and the actual variance. The weight are called beta 1 and beta 2. Those are parameters of the algorithm. Given that this is the update step, so theta k plus 1, so the next parameter is theta k plus 1 is equal to the previous theta k minus eta, which is the learning rate, which is fixed at the beginning of the training, so it's the first learning rate, times this quantity, whose idea is to adapt your learning rate based on how close you are to the solution, times the gradient. So gk is just a summary for the gradient of the loss function here. This, if this term doesn't exist, if you remove this term, you get exactly gradient descent. That's gradient descent, theta k minus eta gk. Adding this term creates an algorithm which adaptively reduces the parameter to get closer and closer to the minima. Okay. Now, this algorithm has some limitations. The first limitation is that it doesn't work. Okay, Adam is a famous example of how mathematics and computer science differ somehow. Because mathematically you can prove that Adam does not always converge to the solution. So there are scenarios where you can show that Adam will not reach a minima at all. Because this term here can amplify or shrinks too much, and you don't get a solution. So you can prove it, there is data proof. But in real scenario, in real application, you almost never meet this scenario, and in practice, this algorithm is the best we've ever had for optimizing machine learning algorithm. It is very fast, it reaches solution in a very few iterations compared to SGD, and it is very not sensitive to the parameter. So you basically can choose whatever data you want, and you will almost always converge to the solution. So it's a very, very powerful method. Everyone in the world used that in the last 10 years, but it doesn't work, theoretically. Okay. So, I think when I was designing these slides, as you can see, there is a missing spot here. That's because I want you to implement it by your own. I decided now that I don't want you to implement it by your own, so I will give you the code because it would take too much time. If you see some missing block in my website, it's because I will update my website with the code after the class. I already have the final solution for this, which is here. Okay. This is the algorithm. I copy pasted into my other code. So, if you want to copy paste my code, you can find it in my GitHub. In my GitHub, there is a file called SGD final, or you can just copy paste it. So I will briefly go through the code to show you how does it work, basically. So the input are the same that we had for SGD. Loss, the graph of the loss, theta 0, the data, that size, the greater than the box. But we also have 3 other parameters, which are beta 1, beta 2, and epsilon. Then we have we initialize the mean and the variance M and V by 0 vectors of the same shape of theta. Here what I do, these losses, it's an empty list to save the loss over the iteration. So it's the one that we call the loss val in the previous function. And that's the whole code. So if you write down the implementation, that's the specialization, that's the core of the code. So what we do is, as always, we shuffle the data, we extract the batch, we compute the gradient, and that's the only difference between Adam and SGD. So if you want, you can also copy paste SGD and modify it. So you update the mean M by taking a weighted average between the previous M and G, and you update V by taking the weighted average between the previous V and G squared. Then you do this operation. This operation is the only reason why this operation helps is because we want to stabilize the first few iterations. Because there is the following, okay? This quantity M and V represents an estimation of the mean and the variance of the of our gradient over the iteration. At the beginning, since you have very few samples, those are very stochastic, they change very, very quickly. So you stabilize them by dividing by those terms. Given that, we just run it forward. Okay? And that's it. I leave you a couple of minutes to copy this code if you want. In the meanwhile, I set up the execution. So, one moment. Okay. If you need me to scroll up or down, tell me. I will scroll up and down or down based on your requests.
Basta così si ricorda anche se scorre guardare questa memoria, un po' di informazioni rimangono nell'embedding. Ovvio, adesso stanno insalagando.
Okay? Let me show you what happens. So let's run the code. Okay? So what I did is the following. I called Adam with exactly the same setup that I had in LGD, so that we can compare one-to-one the performance of the two methods. So now let me plot both loss Adam and loss SGD, loss val, and loss Adam. We did something. Wait a moment. Yes. I append loss to. Okay. What I did now is I add the tab here, so that we append the loss every batch, not every epoch. What happens is that apparently, in this specific scenario, number of iteration of Adam is too high. I believe it was 100. Okay, now it's correct. Okay, so as you can see, number of iteration of Adam is the performance of Adam here are slightly worse than LGD. So one can think, okay, why this happens? And the reason is actually very, very simple. It was predictable, because this problem is a very simple problem. That problem is a convex problem. It's a convex optimization problem. You already know. You should already know, because we did that for gradient descent. That gradient descent algorithm converge in a very few iteration, sometimes only one iteration, in the convex setup. So, in this situation, Adam reducing or increasing the step size is only making it worse, slightly worse, it's slowing it down a little bit. So one can think, okay, so Adam is not that bad, that good. It is. You will see in the next session that Adam is actually very, very better than SGD. But this example was to show you that it's not always the case. Sometimes Adam gets beaten by SGD, but this only happens in very, very simple problems. In practice, with the neural networks and more complicated algorithms, there is no comparison between Adam and SGD. Adam is way better. So now, after the break, we will extend our knowledge to classification, which is the central topic of this, should be the central topic of this class. In Optin classification, we will see that Adam outperforms SGD in practice. So we meet at 10:50.